Okay, good morning, everybody. Welcome to VSPG today. We have a presentation by Dr. Annie Bauer from the University of Wisconsin-Madison, establishing a robust temporal framework for the Paleoproterozoic Lomagundi-Jatuli carbon isotope excursion and the Francevillian Basin's Gabon. Next week, we have a presentation by, let's see, it's right here. Dr. David Catling from University of Washington. His talk is titled Causes and Consequences of the Rise of Atmospheric Oxygen. I'll post that on, I'll send out the announcement for that tomorrow. But after David's talk next week, we have a shift in what time people will be presenting. So after that point, presentation times will be at 5 p.m. for the rest of the year. So I think it's 5 or 6 presentations across November and December that will be the case. So I'll send out reminders for that in email as well. So those are my announcements. And with that, Andre, could you please introduce our speaker for us today?
Yeah, it's a great pleasure to introduce Anne Bauer. Anne is, I presume, originally from Washington. At least she went for double major in Earth and Space Sciences and French and Italian studies at the University of Washington. Sort of quite unusual major, but maybe would be helpful for work in Gabon. And she continued with PhD from MIT. Working with Sam Bauerin. She was a last student of Sam Bauerin, and for her PhD, she focused on 2 topics, studying the oldest crust in Acastanasis in Canada, but also working on a great oxidation event using multiple sulfur isotopes. She continued with a postdoc position at Yale University with Alan Rooney, and sort of at that time she added to uranium-lead system, Rhenium-osmium system for dating rocks. And in 2019, she studied as assistant professor at University of Wisconsin, where she is now. And she will present on temporal framework for Paleoproterozoic Lomagundi-Jatuli carbon isotope excursion in the Francevillian Basin, Gabon. Yeah, the floor is yours, Anne.
All right, thanks so much. Thanks, Alex, and thanks, Andre. First, I just want to apologize, everyone. I have a long-term cold that I've been nursing, so my voice is going to sound a little bit off for the presentation, but hopefully I can make it all the way through. So as Andre was mentioning, my training is primarily in uranium-lead geochronology and actually more from a metamorphic rock perspective. But during my PhD, I got really captivated thinking about the GOE and about applying different radiogenic isotope systems in geochronology to better understanding that period. So the work that I'm presenting today is some preliminary work and then work that's ongoing as part of a recently funded NSF grant that we got from the low temperature and geobiology program. And there are a wide array of collaborators that have been involved in this. And so this ranges from our collaborators in Gabon, from Mathieu Moussavou and Karen Maïka. Karen published a paper that is kind of the original sedimentological and geochemical framework that I'll be working off of today. And then a variety of collaborators at University of Wisconsin-Madison in my group, and then Ivo Lepland, Tony Pravy, Kala Kusame, and Alan Rooney, who have all contributed in various ways to what I'm showing to you today. So the big picture question that really captivated me, actually, and I recognized this at the end of my PhD, which is why I went and did a postdoc focusing on Rhenium-osmium geochronology, was looking at the Lomagundi-Jatuli carbon isotope excursion. And I had never heard of it before the 5th year of my PhD, and then saw this plot in the Lyons et al. Paper that came out, where you see this really pronounced carbon isotope excursion. So we're, again, looking here at time on the x-axis from 4 billion years ago up to the present here. And on this y-axis over here, we're looking at the carbon isotope composition of marine carbonates through time. So you can see that the center is at about 0 per mil through most of Earth history. We don't really know it that well for the Archean, of course. But during this period in time, we have what looks like the most pronounced and potentially most long-lived positive carbon isotope excursion in Earth history. And it follows right after the GOE. And that's evident because you can look at this other y-axis here that's showing the degree of sulfur mass-independent fractionation that's preserved in the sedimentary record in sulfide minerals. And so this is shown in pink symbols in this plot. And you can see that up until about 2.45 billion years ago or so, we are preserving quite a bit of sulfur mass-independent fractionation in the rock record, and then that abruptly terminates. And that's due to rising atmospheric oxygen levels. And so this schematic model below, which many of you have all seen before, is showing how we think atmospheric oxygen may have varied over time. And so this big step here with the transition from preserving sulfur MIF to not preserving it in the rock record anymore comes with surpassing about 10 to the minus 6 times the present atmospheric level of atmospheric oxygen. And you have enough ozone in the atmosphere that you're not generating enough of this signal to be preserving it in the rock record. So something that I hadn't realized before was that concurrent with the Lomagundi excursion, because you need to drive positive carbon isotope compositions in the ocean, you need to be extracting something that's really negative from the ocean. And so the main model for this has been that there's extensive precipitation or formation of organic matter and then storage of it somewhere that can actually drive marine carbonates up to more positive values. And in doing so, you're effectively oxidizing the Earth system. And so you're introducing a lot of oxygen in the atmosphere. And so there's this really captivating language that has been used about an overshoot and crash of atmospheric oxygen levels during this period, where you're having an overshoot during the excursion and then a crash at the end of it when you have this negative carbon isotope excursion. And so I started looking into this more because I was always curious about what kind of geochronological constraints people were applying for sedimentary rocks that are actually pinning out this curve that I'm showing you here. And when you zoom in and look at it more closely, it's not as well defined as that curve in the last plot kind of shows you. So again, we're looking at the same curve. I've switched the direction of the x-axis on you here, and I apologize for that. So we're going from 2.6 billion years ago to 1.8 billion years ago here. Here's a value of 0 for marine carbonates. So here's this predominant excursion. This blue envelope here is to kind of draw your eye into what the excursion might look like, but you can see that if you squint and take that away, it's actually much harder to argue that there's this long pronounced carbon isotope excursion, and there's quite a bit of uncertainty in the record. And the reason for this is because it's really hard to directly date sedimentary rocks. And I'm showing that with uncertainty bars in the x direction on this plot. So the uncertainty in the x direction is not the uncertainty in an age constraint that was obtained, but actually just showing you the range of potential ages. And then the symbol just happens to be in the middle for most of these. You can see I've also color coded this so that green symbols are showing direct age constraints. So again, this is showing you there's a paucity of instances in which we can actually directly date a sedimentary rock that's going to give us information about this carbon isotope excursion. To give you a better sense of how this works, I thought I would highlight an example from the Huronian supergroup because it's kind of a nice, clean example. So many people will be familiar with this stratigraphy, but there are 3 glacial cycles preserved in the Huronian supergroup in Canada. And the positive carbon isotope excursion is up in the Gordon Lake Formation, which is in this uppermost cycle here. In terms of understanding its age, though, we don't have a lot of constraints. And so I've highlighted it over here in this plot with black to show you what the uncertainty in the age of the Gordon Lake Formation was originally presumed to have been. And the lower bound on this is the age of this underlying Archean basement, which is about 2.45, 2.48 billion years old. And then the younger age constraint is the Nipissing diabase. That's about 2.22 billion that cuts through here. So basically saying the Gordon Lake Formation could be deposited at any time during this period. There was subsequent work from the compilation I'm showing you here for getting the age of the Gordon Lake Formation. And so Rasmussen et al. Dated, using uranium lead, dated a bunch of zircons that they interpreted in a tufaceous layer from the Gordon Lake Formation. So here's the distribution of ages that they got from that. They took a select population of those and interpreted that to be a tuff because that's where the predominant number of zircons were of all of the same age and they were relatively concordant. This is what that full data set looks like though. And the main point is that it's just really difficult even to use something that might be a purported tuff and come up with an exact age constraint when you're working with sedimentary rocks. And so that was my motivating factor for looking into the rhenium-osmium isotope system, which I will get into in a couple of minutes. So the larger scale framework here is that we have this potential carbon isotope excursion that may be global in nature. We don't know how long lived it is. I'm showing this coming back to this plot with a red arrow here that's dashed where things are really uncertain relative to the timing and whether or not we're actually recording positive compositions in the ocean at that time. It's solid where we feel more certain about it, and then it's dashed again where we're not really sure about the timing of the end of the excursion as well. So you can see that the proposed duration can vary by a couple hundred millions of years. And this is an important thing to start working out if we're going to better understand what's actually driving this excursion, and does it relate to atmospheric oxygen, and if so, how? There are a lot of other important things happening in the Earth system at this time, which is not surprising because this encompasses almost 1 billion years here in this plot. One that's particularly interesting is this tectonomagmatic lull, where there aren't a lot of igneous rocks produced at this time, which actually makes a lot of this detrital zircon dating really difficult because we don't have a lot of rocks from about 2.3 to 2.2 billion years of age. And so working out certain parts of this record are going to be more difficult than others. There are Paleoproterozoic sedimentary successions all over the world, except for Antarctica, as far as we know. And so where I'm going to be focusing on today is in Gabon in Central Africa, Central Western Africa, and looking at some sedimentary successions that are pretty classic there. But as you can see from this map, there are Paleoproterozoic sediments the world over. A lot of them have been metamorphosed, and so working out information about their original primary depositional conditions can be quite difficult in some cases. And here's a map showing in Gabon where we're going to be focusing today. So we're going to be focusing in the Francevillian Basins. Many of you will be familiar with these rocks if you've ever heard of the Oklo natural reactors, where there was uranium fission occurring naturally. And that's in the lower part of the succession there. So there are 4 subbasins in the Francevillian Basin overall. Today we're going to be focusing on the Latorsville subbasin, but I wanted to show this overall image here first to say there have been decades of work in the Francevillian Basins. Most of the context that I have and what I'm showing you today is going to be coming from one drill core in one of these subbasins in Latorsville. And so I'm going to be working from the geochemical framework that has been recently published from there. But I'm not intentionally ignoring decades of work across all of these basins because I think the correlations across these basins are going to be very important moving forward in the future. What I'm trying to do right now is get really precise age constraints for one locality so that we can better relate all these things together. And so where that fits in is that in the Latorsville Basin, there is a drill core that intersects what we think are probably formations FB and FC. I should have said this on the last slide, but the stratigraphy in this area has been broken up into these 5 general formations, FA through FB. And so we think that the LST core kind of correlates across these 2 units here, but the exact correlation is not entirely certain. Another thing I want to make sure to say is that most of the work that I'm going to be showing you today was done by a master's student who graduated my lab this summer named Sally Stevens, who's pictured on this slide. And the main framework that we set up for this project is first temporal, and trying to understand, can we get precise dates for the end of the carbon isotope excursion, because that's what we actually see intersected in this drill core. And in doing so, can we infer if this is a synchronous event with other places globally, or is it a regional event? And is it happening at the same time, or is it diachronous? And so that will help us figure out if we can tie this to atmospheric oxygenation in this interval. And picking up on that, in using the rhenium-osmium isotope system, we actually get other geochemical information that tells us about how oxidizing the atmosphere may have been at that time. And so another thing that we have been looking at and that I will show you today is trying to probe if atmospheric oxygen levels changed over the course of deposition in this core. And specifically using the rhenium-osmium isotope system, like I was kind of hinting at on this last slide here, is that there are 2 pieces of information we can get. So the first is that we can use the isotopes to get an age, and we can establish that using a rhenium-osmium isochron. But what I'll show you is that we can also use the intercept of that rhenium-osmium isochron, and it'll tell us about the osmium isotope composition of the marine reservoir at that time, which will give us information about chemical weathering and fluxes of osmium from the continents. So for the rhenium-osmium system, I'm just going to give a quick primer. There's a radioactive isotope of rhenium that decays to a stable daughter product of osmium. Its half-life is many times the order of the age of the Earth, but it's short enough that it's tractable to count up the accrual of this 187 osmium over time. And kind of this simplified cartoon that I have here is showing how rhenium and osmium are taken up into sedimentary rocks. And the way it works is that rhenium and osmium are mobilized by oxidative weathering, so they can only go into solution when they're oxidized. And then when they make their way down rivers or whatever into the ocean, and they hit an interface between oxic and anoxic waters, rhenium and osmium come out of solution. Typically, this is in association with organic matter, so it tends to be best to find organic rich sediments to use this system. So they're basically taken out of the water column, they glom onto organic matter or whatever particles, and they rain out, and then they get deposited in a shale, as I'm showing here. So we think about this in terms of isochron space. We can look at the rhenium-osmium ratio of a bunch of subsplits of this shale. If I go take this shale and I sample it laterally as best as I can, or working in a drill core, as you'll see, I have to sample over depth because I don't have the benefit of sampling laterally. And when I do that, there will be varying rhenium-osmium ratios of all these subsamples. Pretend all these little black clusters here are subsamples that I've taken. And that's just variable amounts of organic matter or ways that rhenium-osmium have been taken up into the sediment. But when they all form, they all have the same osmium isotope composition, which is going to be representative of all this osmium that's dissolved in the marine reservoir at that time. So when it first forms, there's this initial osmium isotope composition consistent with marine waters. And then you can fit a line through this, and a slope of 0 is times 0. Then over time, the rhenium decays to 187 osmium. And so you can see a point like this will backtrack this way. I'll move up in the diagram. You'll be decaying rhenium, you'll be producing 187 osmium. And so at any given point in time, we can fit a line through all of our subsplits of shale, and we should get something that gives us a meaningful age. So here's the radioactive decay equation showing this. The amount of 187 osmium in our shale sample at any point in time is that which was originally there, plus that which has accrued through radioactive decay. There are some assumptions inherent in this, though. First is that the rocks have remained a closed system with respect to rhenium and osmium since deposition, which is a difficult thing to test sometimes. And that also all the samples on an isochron have the same initial osmium isotope composition. So if I go back here, that's assuming that this there's an initial osmium that's representative of all of our subsplits of shale. You can imagine that in a drill core, if I took subsamples over too long of a stratigraphic interval, that this might not be true. And that's a difficult thing to figure out how to constrain for the Paleoproterozoic, because we don't know what the residence time of osmium was in the oceans then. And we actually don't really even know it that well today. So then what we need in order to generate an isochron is a spread in rhenium-osmium, so a spread in the x-axis direction that's going to give us better constraints on our age on that line there. And then we need enough rhenium to attractively measure. And so that's usually at least half a ppb of rhenium, which is sometimes, unfortunately, a very tall order in the Paleoproterozoic. During my postdoc, I worked on a lot of rocks from the Onega Basin in Russia that didn't have enough rhenium in them to attractively measure. And so that was obviously very disappointing. But coming into the GOE, we don't have a lot of rhenium and osmium necessarily dissolved in the ocean yet. And so you need oxygen levels to be high enough that there's sufficient rhenium being enriched in sediments to date them, is the main point. Okay, so here is the drill core from the Latorsville Basin that I have been working on with collaborators. This is the stratigraphic column that they have devised for it. And I just want to draw your eyes to some general things. Instead of using the typical FA through FE terminology for the Francevillian basins, they've subdivided it into units 1 through 6, going from bottom to top. The lowest part of the stratigraphy here, units 1 through 3, have sedimentary textures in them that are indicative of shallow marine settings. And when you look at them all in tandem, I don't remember if I mentioned this before, but I have no formal sedimentology training, but I know enough to be dangerous. So if anyone has questions about this, I'm happy to talk about it, but I'm not the sedimentologist on this crew here. So this includes flageur bedding, herringbone ripples, and desiccation cracks. There's also some karst features in these dolomites here, indicating that they were exposed at the surface for a while and there was some weathering of them. And so they've demarcated a transgressive surface here with this dashed line. The part that I'm mostly focusing on and what I've been working on are, with my group, are units 4 through 6 up here. And these appear to be below wave base. They have rhythmites and lamanites predominantly. There's an absence generally of ripples and cross bedding preserved in these units. It also happens to be where the organic rich rocks are, which is why I have focused there predominantly. You'll see that they have a basinal deepening trend as we move up through the succession too. So envisioning kind of a marine transgression over this interval. So the 3 units that we've been focusing on are a pyritiferous organic rich shale here, a dolorhythmite and doloaminite here, and then organic rich shale up top. I'm also showing here the oxygen and carbon isotope compositions of the carbonates throughout this succession that were part of this original study by Maika et al. So that you can see how the carbon isotope excursion plays out in this basin, or in this stratigraphy specifically. So the carbon isotope compositions are shown in bold black here, and you can see here's a value of 0 here and 10 over here. So we have values between +5 and +10 per mil coming up through the stratigraphy. And then as we start to go deeper, there's a sudden shift and it goes down to 0 per mil. And then this uppermost unit here has some diagenetic carbonate in it, and I'll show you that in a minute. So the way that this was interpreted in this publication was that this was a facies-specific preservation of the carbon isotope systematics, and that this had to do with processes depending on where you are in the water column, and that it might not represent the global Lomagundi-Jatuli carbon isotope excursion. I'm not really commenting on that directly today. Instead, the age constraints that I'm going to be sharing with you are going to be relevant for starting to parse this out on a bigger scale in this basin and other basins globally. And so regardless, the age constraints that I'm showing you are going to be relevant for trying to understand this problem. So I said that I was going to show you that this uppermost unit here is diagenetic. So here is what all this carbon and oxygen isotope data, the oxygen data is in white circles here, looks like when it's cross-plotted. So unit 6, which is this uppermost one here that's been labeled as diagenetic, is orange in this diagram, and you can see that it correlates. And so that is part of what's underpinning their interpretation that this has been diagenetic. The units that I focused in otherwise, though, unit 4 doesn't seem to have substantial correlation in it and doesn't seem to be diagenetic. So the 3 places that we took samples are outlined in this figure here. We decided to take one sample of each of these 3 units, and we're trying to pin where the carbon isotope values shift. And so as these carbon isotope compositions are coming down here, we got a subsample of unit 4 just before we reached unit 5. We tried doing rhenium-osmium geochronology on unit 5, but there wasn't sufficient enrichment of rhenium in it. And that might be reasonable to expect. You can see that total organic carbon contents are really low in this unit 5 interval. But sometimes dolomites do have enough rhenium in them, so it was worth a shot. And then we also targeted these diagenetic carbonates up here because they did have relatively high carbon content. And also because I'm not sure if the rhenium-osmium isotope system is going to be reset by diagenesis of these carbonates. I don't think it would, and it's a helpful age check kind of on the lower age constraint that we were trying to obtain. Something I forgot to say a minute ago too is I've popped open more of this plot here, right? And so I'm showing you more information. So here's the carbon isotope composition of organic matter throughout the succession. You can see in this diagenetic interval up here, it gets very negative, which they interpreted as indicative of presence of methanotrophs when we're getting to deepening waters here. We're also looking at the concentration of manganese in percent shown by these yellow diamonds here, or you can look at the manganese calcium ratio by these black diamonds here going up through the succession. And you can see generally with the manganese calcium ratios that they're increasing as we're getting into the deeper in the basin. So an important interpretation that's part of this that's also consistent with stratigraphy elsewhere in the Francevillian basins is that there's more manganese enrichment up higher in this succession, which is indicating potentially a flux of nutrients or some hydrothermal influence coming in. And we'll come back to that toward the end of my talk. But let's jump into the geochronology. So here's the first isochron that we got for this depth here, where we're going from about +5 per mil to 0 per mil. And you can see this was probably a pretty disappointing result for a geochronologist. There's quite a bit of scatter in this diagram, right? You can't just fit a line through this data and say, here's what the age is. But it ended up actually being kind of an interesting story. So what I'm going to do is spend the next several minutes kind of walking you through how we've taken this information, we've actually tried to interpret an age out of it, and a story for what has happened post-depositionally to the rhenium-osmium isotope system such that the data looks the way it does here. In this plot, I should say every subsplit that we took, so this was over about a 30 centimeter interval in unit 4 of the core. Every subsplit has its own name here. And if we replicate it with analysis, there's an R next to it. So 52.71 and 52.71 R, the same sample, same powder, we've just analyzed it twice. When you're looking at this data, you might notice that if you take an upper limit to it, you can fit a line through it, right? And so I'm just showing this very schematically here. And this is kind of compelling your eyes drawn toward this and say, is there any sort of age meaning to this? And what happens with all of these data points here? Why are they not falling toward this line? So the way that we kind of stepped back and started thinking about it was in calculating the initial osmium isotope composition for every single one of those analyses at about 2.1 billion years ago, which is a good age constraint for this basin based off of pre-existing geochronology that I'll come back to later. When we do that, I'm plotting that value on the x-axis here versus the depth that we integrated. So going through about 30 centimeters of core here, you can see that there's actually a localization of where initial osmium isotope compositions that are actually geologically possible are located, which are these ones I'm showing in green here. They're all greater than 0. It's impossible to have a negative initial osmium isotope composition. That's not physically possible. And so you can see that at this shallower depth here and this deeper depth here, is where we're kind of seeing parts of the shale where the rhenium-osmium isotope system clearly has been disturbed. So if we go and look at this texturally, this wasn't something we were really expecting. You can see that there are some different character to these rocks depending on what depth we're looking at. So the ones that are preserving initial osmium isotope compositions that are geologically plausible happens to be really pyrite or sulfide rich part of the shale, which is something we weren't really expecting. We were mostly trying to avoid any sort of major amount of pyrite or sulfide or any sort of veining of our samples, but we were kind of required to sample this part of it because it was the only material that we had to work with. And it, strangely enough, it ends up actually preserving some systematics here, and we'll come back to that in a second. The shallower part of the core and the deeper part of the core tend to be a little bit more friable. They don't have as much sulfide preserved in them. I don't know if that's a primary feature or not. There's also quite a bit of carbonate associated with these that seems to be secondary. We can also look at the concentration of rhenium of all of these subsamples. And so I'm doing that in this plot here at the left. And so again, if we plot that across against the initial osmium isotope compositions, you can see that predominantly for subsamples with lower concentrations of rhenium, and then they seem to have been more susceptible to some sort of alteration or post-depositional behavior. So we come back to the isochron and we use this color scheme that I've shown here to kind of segregate by depth what subsample or what depth every subsample is from. You can see that everything that falls off of the purported isochron here are from those depths where we are from those depths that don't have as much sulfide preserved in them. So we take this regression through the data that does have initial osmium isotope compositions that are geologically plausible. We end up with an age of about 2.1 billion years ago. And what I wanted to do next was kind of show, well, what might be going on with this data that's sitting off of the isochron? Why is it over sitting here to the right? Why does it have these geologically impossible negative initial osmium isotope compositions? And basically what this requires is an increase in the rhenium-osmium ratio of all of these bits of shale after deposition at some point in time. And that moves them to the right off of this isochron. When you do that, if you regress a line through them, as I'm trying to draw with my cursor here, the intercept is going to end up being negative because it's going to be intersecting down here somewhere. So as I mentioned before, some of these samples were analyzed in duplicate. The reason they were analyzed in duplicate is because when we analyzed them, they fell over here into this space. And so we thought, okay, let's just analyze them again and make sure this wasn't some sort of analytical issue, even though we couldn't really figure out what an analytical issue might have been. The data looked fine. So in this example, here's one that's a repeat of the same analysis here, but we'll just kind of zoom in on those only. So for the repeat analyses that fall off of the isochron, I've tied a line between those two repeats so that you can see where they fall in this space. So the first thing we get from this is that most of these lines are horizontal. So right away, this is telling us this is probably a relatively modern process. If it was an ancient process, we'd see more of a slope associated with these, but because they're relatively horizontal, that's saying that this has happened in relatively recent geologic history. Again, what consistent with what I was saying a slide ago, this also requires an increase in the rhenium-osmium ratio because it's moved everything to the right of the isochron. We don't see any data sitting over here on the left-hand side of it. So in order to increase the rhenium-osmium ratio, you either need to kick osmium out of the system or add rhenium to the system. So we're looking here for either osmium loss and or rhenium enrichment as processes contributing to this. Another thing you might have noticed is that we've repeated the same sample powders sometimes and not gotten the same result, which is a little bit disturbing. And we were confused about this at first, but I think what it's telling us is either that we didn't powder our samples to a fine enough scale such that we're seeing kind of nugget effects. But I think from some laser ablation ICP-MS mapping that we've done, and I'll show you that in a couple of minutes, there might actually just be a nugget effect where the amount of rhenium and osmium in these samples is small enough and it's enriched in really concentrated domains within the shales that's actually hard to powder them to a scale where you could repeatedly reanalyze them. When we were looking at this more carefully, we were trying to discern if this was rhenium gain or rhenium enrichment or osmium loss from these samples. And so I have here listed the ppb of rhenium of repeat analyses. And what you'll notice is everything that's on the left-hand side is a lower concentration than the one on the right-hand side for all three of these pairs here. And so what this is indicating to me is that the further away you move from the isochron, the higher amount of rhenium you actually have here. And so that might be indicating that rhenium enrichment is the predominant process. Overall, this is relatively consistent with modern weathering studies, which are trying to understand the osmium isotope evolution of the oceans, which have shown predominantly that rhenium seems to be more mobile in the modern environment, weathering out of organic rich shales than osmium, which is a bit surprising because osmium has 7 different oxidation states and is a little bit squirrelier than rhenium. But there has been extensive documentation of this in modern weathering profiles. So to come back to this idea of inhomogeneity of sample powders, we want to understand this better. And this is something we were hoping to do anyway. We wanted to see if there was a way petrographically and texturally if we could look at our samples and assess if they were going to be good candidates for rhenium-osmium isotope analysis to begin with. But luckily in doing this work, we're actually getting more information now also about disturbance of these systems. So this was the inspiration. This isn't data that we've produced. This is actually from the Onega Basin, Russia, from a recent paper by Carl Mond. And this was our inspiration essentially for what we ended up doing. So what they did here is they took an optical image. I think this scale bar here is about 1 centimeter long. And you can compare this across these 3 different plots here, which are images here, which are showing the distribution of redox sensitive elements in the shale. They looked at molybdenum, rhenium, and uranium. And you can see these are just colored by counts per second. And so what they were effectively trying to do was demonstrate primary authigenic enrichment of these redox sensitive elements in their shales. And the way that they wanted to do this was show that there was random distribution of these elements throughout the shale texturally. So we were hoping to do the same thing. You can see that these 3 elements do not all behave the same. I mean, they're not coming from the same sources. They're not enriched in exactly the same way in these rocks. And so they're all carrying different types of information, which is why we wanted to target all 3 of them. So in my lab at University of Wisconsin-Madison, I inherited a femtosecond laser ablation system from Clark Johnson when he retired. And so we've been using that in tandem with an Agilent triple quad ICP-MS that I purchased shortly after arriving. And we're using this to try to map out the distribution of rhenium, molybdenum, and uranium throughout these sediments. This is a bit harder to do than we had originally realized because you can show counts per second maps like I showed on that last slide, but the problem is that there's differential ablation of phases. And so we've been working really hard to try to normalize to that and standardize that in a way that we can actually get meaningful concentration distributions through the shale. Because as you can imagine, organic matter is a lot fluffier than like a detrital mineral. And so the way that those ablate and respond to ablation is really different. So I have some preliminary data to show you for this today. I don't have as much as I would like to show you, but this is something that we're actively working on. And this is mostly something that researcher Athena Eister and researcher Mike Tappa have been working on in my lab. So I'm showing here 2 different samples from the Francevillian Basins, from the LST drill core, where we took parts of our shale that we were not going to analyze for rhenium-osmium isotopes because there were some sulfide layers in them and we thought we didn't want to analyze that part of them. And so we looked at these little chips and we have optical and BSE images of them. And then we have made laser ablation maps of just molybdenum and uranium. And I've done this for enrichment factors here, so normalized to aluminum. And the reason we don't have rhenium yet is because we have 1 to 2 orders of magnitude less rhenium than in the previous study I showed you that kind of inspired this work. But Athena and Mike have actually recently cracked how to do this by increasing dwell times. And so that's something that we'll have forthcoming. What you can see from these maps is that where the sulfides are localized in this sample here is where the molybdenum is mostly localized, but there are also hotspots of molybdenum out through the shale as well. Uranium is more randomly distributed, and it's hard to know which part of that is a detrital component versus an authigenic component. But what we're mostly looking for is that there hasn't been major redistribution of these and localization into veins and things like that. And so a lot of the work that we're trying to do is take the parts of our samples we would never touch for rhenium-osmium and better understand how these elements are being mobilized into silicate and pyrobitumen veins and that kind of thing. It's a better example over here on the right where you can kind of see the distribution of these along sedimentary layering too. All right, so effectively what we've shown is that there has been enrichment of rhenium in the modern system, relatively modern, in this unit 4 subsample that we looked at. That's about a 30 centimeter sample of drill core. But some parts of that drill core, the ones that had sulfides in them, tended to preserve original rhenium-osmium isotope systematics. And so our age interpretation for this sample is about 2.1 billion years ago, or 2107 million years ago. I think what this might mean is that the sulfide was early enough that it could take up the rhenium and osmium and kind of lock it in and protect it from later fluids that may have come through that may have oxidized the rhenium and enriched it, or enriched rhenium in these other parts of the shale, just on either side of these subsamples here. To corroborate this age, we got an age, as I mentioned earlier, up in this unit 6 here, where there's diagenetic carbonate. Nothing fell off of the isochron there. This was actually relatively well behaved. And so we got an age constraint of about 2085 million years ago there. These two ages aren't within uncertainty with one another in terms of the external uncertainty or internal uncertainty, but they are within uncertainty with one another in terms of the external uncertainty. But essentially, there's a base stratigraphic order, so that gives us a little bit more confidence in the age constraint that I showed you in the last slide. So as I mentioned earlier, I don't know if diagenesis is going to be impacting the rhenium-osmium isotope system and redistributing it. And so could we get a potentially younger age for the sample because of that? My suspicion is that this diagenesis is early enough, right? Because it's happening at the sediment water interface, that these uncertainties just kind of swamp out anything that would matter for that regardless. Okay, pardon me, just needed a bit of tea. The next thing I wanted to do is just show that our ages in the context of all the pre-existing geochronology for the Francevillian basins. And this is a really cool problem. The Francevillian basins have had a variety of geochronometers thrown at them and a really creative use of a lot of these. And so I just kind of wanted to walk through them so that you can see all the hurdles our community has to jump over to try to get age constraints on this succession. So the first one is there's some intrusive cyanites in the FB formation. So we're going from the stratigraphic order from bottom toward the top here in this diagram here. And I'm just going to kind of stack in these age interpretations as we go. And this is a rubidium strontium age. And you can see the data here and then this one here. So everything's kind of pinned on this one up here. And it's not very precise, but it's about 2.1 billion years ago, plus or minus 150 million. And so that represents a minimum age because that's intruding for the FB unit because it's intruding into the FB unit. This was revisited a few years ago by Sawaki et al. They looked at an intrusive granite also in this unit, and they looked at the zircons in the granite. The data is actually quite complex. Here's a uranium lead Terra-Wasserberg diagram showing this. All of these little gray circles here are showing zircon analyses for which there was quite a bit of common lead in the zircon, so it was very hard for them to work out a primary age from this data. And you can see that these are very discordant for the most part. So down here is a plot from their paper where they plot the 204, 206 lead isotope composition versus the 207, 206. They take the intercept of that for a subset of that data to say, if we unmix the incorporation of common lead from these, so we need to unmix the 206 from that common lead, and we're using 204 as a proxy for that, what is the age for that? And so their age constraint is more precise, about 2191 million years ago. Then as we step over, this is the one that I actually really enjoy. For this paper, Bros et al. Separated out different size fractions of clay to interpret a diagenetic age from the clay. And so they use the samarium-neodymium isotope system. Here are two different isochrons where they have done that. These are these two age constraints here. So not very precise, but dating the timing of diagenesis in the FB formation. Then up in the FD formation at the top of this stratigraphic sequence. So I should have said earlier, this isn't strictly in the Latorsville Basin. This is kind of dispersed within the Francevillian Basins. There are some zircon age constraints. So I'm showing two of those here. The one that's most well known is from a Goldschmidt abstract from 2005 by Hori et al., where they have some shrimp uranium lead isotope constraint or dates for zircon. And you can see that there's a variety of zircon ages that are concordant here. There's some that are discordant. And they interpreted this concordant population here of about 2083 million years ago to represent the youngest age in the succession, and therefore the maximum or the youngest age of the zircons, therefore the maximum age of the FD formation. This was reinterpreted by one of the co-authors on that study about 11 years later, and they actually took this array of more discordant zircons here and said some of these are actually younger. And so if we can interpret these as being younger, but actually still valid preservation of uranium lead isotope systematics, then the youngest age got revised to about 2 billion years ago. And so that's a pretty substantial change there in that age interpretation. So the picture that I'm painting here, right, is that there's a lot of complexity and it's really hard to date these rocks directly. And so effectively what we've done here and what I'm showing you today is that the rhenium-osmium isotope ages that we have gotten are more direct age constraints for the FB/FC units, where whatever the Latorsville Basin core that we worked on is sampling. So I'm showing the internal uncertainties with the bounds of these blue boxes here for unit 4 and unit 6. And then the uncertainty bars are actually showing the external uncertainties. So that's if we wanted to compare across labs or across different isotope systems. So in the context of the data in this plot, you would be looking at those external uncertainties. If you just want to compare this age constraint to this age constraint, that we can use the two blue boxes there. So the next steps in this is that we're broadening our approach to basin beyond Latorsville and also within Latorsville, there's an ICDP workshop for drilling in this region that's coming up in about a week or two that my research group is going to be attending with a lot of our collaborators and probably a lot of people on this call. And so we're excited to figure out how best to extend this and work out a more precise framework within subbasins and then correlate across basins, and then also more globally. And so coming back to this plot that I showed near the beginning of my talk, I showed this original age constraint here. I think I actually forgot to talk about it, but the bounding age constraint was that this was at least 2083 or older million years ago. And this green data is showing what our new age constraint for the end of the carbon isotope excursion in unit 4 is pinning this as. And so we can go do this incrementally in some places throughout the Paleoproterozoic. We might have a better stitching together of this curve and a better understanding of the global versus regional extent of this carbon isotope excursion. Okay, so that's the temporal part of the story. With the time I have remaining, I'm going to go through the oxygenation part of the story that I mentioned earlier. So in the drill core, we analyzed these two depths here. You may have noticed, I didn't show it at the time, but for both of these isochrons, we have different osmium initial isotope compositions for the marine reservoir. Deeper in the succession at 2107 million years ago or so, we have a value about 0.42. Shallower in the succession at about 2085 million years ago or so, we have a value of about 0.25. So there's some change or shift there, and that's something that we're going to kind of probe into further here. So the main question is, what do marine osmium isotope compositions tell us? And this cartoon here shows this really nicely. The fluxes of osmium to the ocean are predominantly hydrothermal. So at mid-ocean ridges and coming from the mantle, we have values of about 0.12. Cosmic dust is coming in too, and that's a more minor contribution to the oceans. And that's a value similar to the mantle hydrothermal flux. And then the third major contributor is crustal weathering. So if you can oxidize osmium and dissolve it and take it in solution in rivers out to the ocean, then you're actually bringing in a more substantial flux of osmium there. The modern value of this in rivers is really high relative to the mantle value. It's about 1.5. Measuring the difference between 0.12 and 1.5 is trivial on most mass spectrometers, right? We don't know what it was in the Paleoproterozoic, but we know that it would have been radiogenic relative to the mantle, and that's the main point. And so by sampling anoxic muds or looking at organic rich sediments, we're actually kind of probing the mixture of all of these things into the oceans. So if atmospheric oxygen is not turned on at all, then we should expect to see a value close to about 0.12, 0.13. If you have atmospheric oxygen available and you have oxidative weathering turned on, essentially, you should see much more radiogenic compositions. And so effectively, that's what we're seeing, right? These values here, 0.25 and 0.42, are telling us, okay, there is oxygen in the atmosphere. We're delivering osmium via rivers that's oxidized, but there's a change in it, and that's the thing that I want to understand next. So I'm pulling up here a schematic diagram from the Maika et al. Study showing that as you progress up through the Latorsville drill core, you see this marine transgression. So each of these three little time points here is showing where you are in terms of the bottom, where you're sampling the core and where the redox cline is with respect to that. So lower in the core, we're sampling these shallower units here. As we move up through the core, we're going to sample unit 4, which is where my first Geochron subsample is. And then at the top of the core, we're sampling the deepest units. That's all part of this marine transgression that's kind of progressing up through this figure here. So part of the story that I mentioned earlier is that the manganese enrichment starts kicking in and becoming more pronounced at some of these higher stratigraphic levels, which is when we're in deeper waters. And so this cartoon up here is trying to show this. Where you have dissolved manganese that's reduced, coming from hydrothermal systems and coming from deep water upwelling. As it reaches the redox cline, it is oxidized and it's precipitated out as hydroxides, and then ultimately gets incorporated into the carbonates there. So the interpretation of the Maika et al. Study was that there was actually enhanced delivery of nutrients during this time, because we actually see in higher TOC concentrations overall, and we also see higher productivity generally. So this shift may be consistent with these, and I'm going to come back to that in a minute. But the way I was initially thinking about this and the way that we'd initially constructed the study was thinking about oxygen levels and saying, if the osmium isotope composition in the marine reservoir changes, it's due to oxygen. And so I'm showing that really schematically in a cartoon here. So our original hypothesis was that if oxygen levels in the atmosphere drop, therefore oxidative weathering rates would drop, and you might expect to go from a value of about 0.42 at 2107 million years ago to about 0.25 at 2085 million years ago. So the implication is the flux of hydrothermal osmium is the same at both of these time points, but that it's more substantial for oxidative weathering earlier, and then that's actually decreasing over time. I realized though that to test this, that we needed to make sure that we had the same provenance. So the things that were weathering locally into this basin were not changing substantially over this interval. And so something else that Sally did for her master's thesis was look at the neodymium isotope composition of the clastic material in these units to make sure that it didn't shift substantially. So here's what her data looks like. We're looking at epsilon neodymium at about 2.1 billion years ago with stratigraphic depth. So here's her unit 4 samples. That's the deeper sample at 2107 million years ago. And then here's unit 6 at 2085 million years ago. And you can see that these are slightly different, but they're essentially the same. They're both about -10 epsilon neodymium. For reference, I have some local basement compositions plotted here, and then you can also see the FA and FB formations. It comprised quite a large range of epsilon neodymium compositions, but generally the provenance hasn't changed significantly in the depositional interval that we're looking at specifically. There's a much richer story for neodymium isotopes here that we're working out still, and we're doing some more analyses to kind of check this all out. And so I'm excited to be able to share that with you in the future. So coming back to this hypothesis, that was that first hypothesis A, that oxygen levels drop. And the provenance does seem to be the same, so that could be consistent with what's going on here. The alternate hypothesis that I already hinted at by showing you that diagram from Maik et al. And talking about manganese enrichment is that maybe it's the oxidative weathering flux is actually staying relatively similar over this time period and oxygen levels haven't changed, but it's actually the hydrothermal flux of osmium that's changing substantially. And I'm trying to show that schematically with a thicker arrow over here, where maybe the flux that's coming from the crust and the provenance that you're weathering hasn't changed substantially, but the amount of osmium delivery from hydrothermal systems is actually greater. Because it's a lower value, it can pull down the value being recorded at the locus of deposition here. So as I mentioned earlier in my talk, the difficulty is we don't have a good understanding of the osmium residence time in the modern oceans, much less back in the Paleoproterozoic. And so it's hard to know how that is going to be impacted by upwelling, deep upwelling and more hydrothermal flux coming in. And if it's a short enough time scale, that actually works. If it's not a very short time scale for the osmium residence time, then that hypothesis actually wouldn't be viable. So coming back to the kind of overall context here, this is the Maik et al. Stratigraphy, and we've basically provided an age constraint for this shift here in the Latorsville Basin in Gabon. And we've also provided an age constraint up for these diagenetic manganese-rich carbonates. And again, that's where we're seeing most of this manganese enrichment in these rocks. And so that might indicate that second hypothesis of upwelling might be a more reasonable explanation for why the osmium isotope composition shifts in the marine reservoir. Okay, so just a quick little plug for the next steps that we're working on is the proposal that we've been working on. We are comparing the successions in Francevillian Basin, and looking also at the Onega Basin in Russia, and trying to better understand if these are contemporaneous systems. And so this historically, these two have been compared and assumed to be contemporaneous. And that's shown here from this paper from 2011 by Lee et al., where the organic matter carbon isotope compositions have been matched up in terms of their profiles for the Francevillian Basin and also for the Onega Basin down here on this x-axis here. But you can see here that this has stratigraphic depth here, and then this is just kind of like stretched out to match this. And so it's just showing that the magnitude of shift of the carbon isotope composition in the organic matter that's preserved is a similar excursion, but it doesn't actually give us any temporal information. So this is something that we're trying to test further. So we have one preliminary age constraint that I got while I was a postdoc at Yale. So here's the Francevillian Basin geochronology that we've already walked through. Over here, we have the Onega Basin. Again, we're going stratigraphic order from bottom to top in this direction here. The green interval in both of these plots is trying to show when we think the end LJE or the shift in the carbon isotope values might be. And so this window is permissive of that completely for the Latorsville Basin. In the Onega Basin, it's less clear. So the age constraint that I have so far from the Onega Basin post-dates the shift from positive to zero carbon isotope compositions and carbonates. And so we don't actually have a very good constraint on it. And so these dashed lines are kind of showing the permissible interval. So for the time being, our best understanding of this is that they could coincide in time. We don't know if we're gonna be able to get good enough precision to kind of compare these or say definitively whether or not they're synchronous. But that's something that researcher Athena Eister is working on currently. A quick plug for Athena too is that she's gonna be starting as a professor at Tufts University next fall. And she and I are both actually looking for people to work on this project with us. And so there's an opening in a graduate student in my lab right now. If you know anyone good, please send them our way. All right, so the take-home messages from what I've shown you today is that we set out to date the end of this carbon isotope excursion in Latorsville, and we got kind of this wonky data here. But by going and looking at it more closely and actually doing these repeat analyses and seeing this heterogeneity in the sample powders, it actually revealed quite a bit more wealth of information about how the rhenium-osmium isotope system has been behaving post-depositionally in these sediments, which could be really important for further work that we're planning on trying to better understand some of these systems where there's complex preservation of these systematics. So the direct age constraint that we have here, I actually had this wrong, this is 2107. Plus or minus 2.4 or 5.0 million years ago for the end of the carbon isotope excursion preserved in the Latorsville Basin. And then finally, we saw a shift in the osmium isotope composition in this succession with time to less radiogenic values, which could either be consistent and be tracking falling atmospheric oxygen values, but it could also instead be tracking an increased flux of nutrients and upwelling of deep water in the system. And with that, I would be really pleased to take any questions you might have.
Thanks, Annie. That was really great. I'm thinking a lot about rhenium-osmium now. So we have one in the, someone sent me a message during the chat, but so for now we're going to transition to our question part. So you can raise your hand or you can send them, type it into the chat and I'll ask it for you. So our first one is from K Sender Sarwan as a direct message to me. It says, so do extinct radionuclides found in meteorites and embedded to the Earth via meteorite collisions have an effect on the rhenium-osmium ratios?
The rhenium-osmium ratios of the sediments or the ocean?
That's sort of all it has. I'm guessing it's sort of a question on about the ocean, probably relevant to the cosmic dust or something.
I'm not aware of what extinct radionuclides they're asking about, but I think, let me just pull up the relevant diagram for this. I think what they're asking is about this cosmic flux. And so what I can say is that we don't have a good understanding of how that may have varied over Earth history. You certainly may have expected it to be much higher in the early Archean especially. But if for that to matter in terms of our interpretation of the stratigraphy we're working on, it would either have to change substantially over like a 30 centimeter stratigraphic interval to change the initial osmium throughout that, and that would affect our ages, or to change between like the 20 meters of stratigraphy of these two age constraints that we have. And because there's not a lot of, there's no like cosmic material or preservation of any sort of like impact evidence through this stratigraphy, we're not too worried about that being a major player here. I'm not exactly sure if that's the question that was being asked, but I think that's probably the relevant information related to this.
Okay, thanks.
Yeah.
I have a question I can ask.
Sure.
So I'm curious about this 187, 188 osmium in modern systems. Do we have a sense of how much it changes in modern basins, both restricted and unrestricted?
Oh, that's a great question. I don't know about that. I know about it for strontium isotopes more, and strontium has a much longer residence time than osmium. It has a residence time of like 1 million years, and you can see complex systematics in restricted basins and estuaries. So I'd imagine for something like osmium, which has a residence time that we haven't agreed on completely, but we can agree that is like tens of thousands of years, I would imagine that there would be complex systematics. And so that's part of the reason that the way I was trying to couch this is that we need to think about this on a basin by basin scale. And if we're thinking about it just for one drill core at a time, it's actually easier to think about the localization of that. I think you're getting onto something really important there though, Alex, that I think this could change substantially if you have different degrees of restriction.
Yeah, I guess whenever I'm thinking about these, when we try to show things with a diagram with a redox-cline, we can think about if that redox-cline represents everything or if it represents local conditions.
Yeah.
And it's, you know, it depends on the system whether or not that question is really important. So I guess it would be interesting to see if this osmium is highly variable in modern systems too.
Yeah, that's a great question. I'm sure that's something that Bernard Poker-Ehrenbrink or Greg Revisa has probably looked into, and I'm just not as familiar with the modern literature. But yeah, I like that question a lot. Thank you. For thinking about this system, I think the way forward might be getting more drill core up and down section of this too, if we really wanted to understand this better, right? But the problem is that you can see with these uncertainties on the ages that we're never going to get low enough age uncertainty to answer that in a really satisfying way in ancient past, right? So I think you're right that the modern might be the better way to start thinking about this.
Okay. Andre, do you have a question?
Yeah, maybe I can ask. I have actually two questions or comments. So first one on initial ratio. And I started, so we looked also the same drill cores, and we looked this level with sulfides. And so this are certainly, sulfides are not in veins, so we're not very late of time they formed. But on the other hand, in this organic rich shales where there are no pyrite nodules that kind of would bend lamina around them as they formed very early on. So this pyrite sort of look like a disseminated and like a matrix in filling a space between grains rather than sort of pyrite nodule growing and displacing grains before they were lithified and compacted. And so that could have a relevance to your initial ratio in the sense that it's possible that sulfidic layers would be formed later. And we had a similar problem in a paper we published with Holstein and Judy Hanne, where we analyzed sulfidic organic rich shales, Archean organic rich shales, and they ended up with age that was approximately close to depositional age, which is not very well constrained, but around 2.6, 2.7. But initial ratio was quite radiogenic. And we sort of explain it by some sort of very early impact on Rhenium-osmium system that kind of affected initial ratio, but did not affect age so much. So with this, I probably be more confident maybe in your second age, but I guess we both live in Erebus. And that has implication for your arguments, application of initial Rhenium-osmium ratio, because it might not be carrying environmental significance, but might reflect this sort of mode of formation or timing of formation. And it's relevant because when we dated Timble Hill and a few other isochrons came, surprising feature was that initial Rhenium-osmium ratio, initial osmium ratio was in Paleoproterozoic non-radiogenic, and even after you couldn't really explain it. And there are new data that might be showing more radiogenic examples, but we also have isochrons that are not very stable. So that's something I worry a lot. So maybe
thank you for that comment. I think what's compelling about this data, at least, is that the initial is really consistent. And so if sulfide formation, and there's different textures of sulfides in these, as you noted, right? There's nodules and there is disseminated sulfide. If the sulfide formation was causing the initial osmium to vary because you're rotating the isochron in some way, you would expect it not to be so homogeneous, right? It would depend on what, like if you subsampled certain textures or avoided certain textures of the sulfides when you were subsampling for the Rhenium-osmium isotope system, you would expect to see variation in that. And we don't really see that, right? We see these are all pretty consistent values. I don't have a good plot showing this, but actually the fit of this isochron shows it really well, right? The MSWD is a pretty low, reasonable MSWD. We have very low uncertainty compared to the other isochron, and it's saying that this is a really repeatable initial. So if what you're talking about is the case, you would have to be sampling it very consistently through that entire stratigraphic interval in terms of the textures of sulfide that you're hitting. I've read the paper that you're talking about. I don't remember this part of the interpretation though, so I'm glad you're bringing this up, and I'll look back at that and maybe we can follow up too.
Mm-hmm. Cool.
And you said you had a second question too, or comment.
Yeah, and second, maybe just to push you on sort of previous talk by Tony. So he suggested that where transgression, sort of contemporaneous deep water and shallow water fascias were having different carbon isotope composition, and transgression would kind of bring this apparent end of excursion, which has nothing to do with global signal. So your ages consistent with accepted end of Lomagundi excursions. So how does it fit to this argument?
Yeah, I mean, the sad thing about the ages is that they're just not going to solve this on their own, right? And that if we have more precise geochronology everywhere, we might be able to start seeing whether all these things are permissible being synchronous or not. It's possible that that won't pan out. But right now, the age constraints that I've shown, are consistent with when we think we're seeing this in other places. We haven't actually precisely dated it really anywhere else that well, I think. And so that's kind of where my future plans are for this, is trying to keep tackling this from that perspective. But as I showed you at the end, it is permissible of being synchronous with the Onega Basin, but like the degree of time uncertainty here is huge, right? These are 75 million years here. So this is almost 150 million years here, corresponding with this envelope here too. So in order to parse out the differences between these models, I think it's going to take some real luck in terms of what we date and whether or not they overlap. But I do think that Tony's model is compelling, but I think in order to test it more, a lot of the plots in his paper relied on the existing Geochron, which is not very precise for most of these places. And so until we can better parse that out, I don't know how we're going to answer that. But what's nice about the age constraints that we got is that regardless of what model you're looking at, they have relevance for this shift in these successions. And I guess if we, in response to Alex's question a couple minutes ago, I was saying it would be nice to drill up and down section of this in the Latorsville Basin, and that would be a nice test on some of this. And so that's something that I've been thinking about. But I don't know if the age precision will be good enough to really test it.
Yeah, just a comment with on the Scandinavian shield in Finland, there are several age constraints. Sorry, my dog is barking. For when the Lomagundi excursion, and we are kind of from different basins, but sort of we are between 2.11 and 2.06. So your age constraints would be within it. It doesn't resolve obviously the question, but it's at least not inconsistent. Yeah,
I agree. I think, and it's possible we won't be able to resolve it, sadly, too, right? But it is consistent with both right now.
Okay, thank you.
Okay, so I have a couple in the chat. I'll ask another one from case_1 because it was relevant to what was just being discussed. He said, is there any intrinsic properties of sulfides and associated, or he says, and allied minerals that makes them that can alter the osmium ratios in certain instances?
I think the way that you would do that is having oxidizing fluids come in later and remobilize rhenium and osmium from those. And it could happen anytime post-depositionally up through the present. And that can lead to rotation of the isochron or some of this anomalous behavior. And so there could have been sulfides in these depth intervals here that no longer seem to have much sulfide in them. And so it's possible that rhenium enrichment or removal of osmium could have happened if there had been sulfides there. But because we think it's rhenium enrichment, I think that's less likely as a process. That's not a very satisfying answer, but I think it's generally just through oxidizing them and breaking them down.
Okay, and then Benjamin also asked something that's also relevant to this point. Thanks for the talk. I was curious about how osmium would be transported in anoxic water, say from a hydrothermal source. I thought I heard you say rhenium and osmium are soluble in oxic waters and insoluble in anoxic. Thanks.
Yeah, that's a good question. We know that there was some flux of it and that there was some osmium dissolved in the ocean despite it being anoxic. That's a good point. In the Archean, because the rhenium-osmium dating that has been done on organic rich rocks, mostly by Brian Kendall in the Archean, has recorded unradiogenic values of about 0.1. So there is some osmium making it through the system despite that. So I don't have a simple answer to that, but I think it might also be that osmium is really particle reactive, and so is rhenium. And so in the modern ocean, you see a lot of rhenium in association with seaweed. So if you have organic matter, things like that, maybe clays, you can actually take it out of solution more effectively. But if you just are transporting it through the water column and you don't have something for it to react with, that it maybe doesn't have anything to glom onto, and that might be the difference.
Paul has a question. What is the depth of the chord interval below the present weathering surface?
The weathering surface is just above where it's showing here in the stratigraphy. So this unit 6 actually is weathered. So it's not that far below overall, honestly.
Yeah, it's actually a good question. So most of these drill cores are quite shallow, and it's a tropical country. So it's, I mean, we're certainly solid, but waters can penetrate pretty deep in this tropical climate. And to some degree, you show it with samples that you rejected, where kind of organic matter getting oxidized.
Yeah.
How bad is it for trying to do this on, like, say, just if all you had was outcrop? Would you just like not do outcrop samples at all?
I would be worried about doing it. I have tried some outcrop samples for the Huronian supergroup, and it's the preservation of rhenium within a layer is really variable across the layer in a way that makes me worry, where you might have like 26 ppb rhenium here and 0 ppb rhenium right next to it. And I think it's just really hard to get fresh samples, right? You can break off and get further back in the outcrop, but drill core seems to be the best answer for a lot of this. The problem is that you don't have that lateral information, right? And so you're forced to do what we did here, right? Which is work over 30 centimeters of stratigraphy, and who knows how much time that represents, but it's probably quite a bit of time depending on the deposition rate. So I didn't mention this, but the depositional rate that you can calculate between these two Geochron subsamples are actually really slow, like unreasonably slow too. So that might indicate a break in deposition between them too. So we just don't have a very good idea.
Okay, well, since there aren't more hands up, I guess maybe I can pick your brain a little bit about this rhenium-osmium system, and I might be showing my ignorance of it here. But anyway, I know that it gets worked on in these organic rich shales, and that's generally the like target, I guess. But what it looks like here is a lot of it being well preserved by your early precipitates and even diagenetic stuff. So I guess generally you wouldn't target carbonates because you can't confirm how, I mean, they're not like collecting a whole lot unless they were really like, sorry, anoxic, right? So you need anoxic sediments essentially. But so why, I mean, I feel like from seeing this, it looks like early diagenetic precipitates or like early cement should be really the target. Can we do this with early silica cements, sort of oxide cements and such like that? Or
yeah, it's
is
a great
it really just these anoxic shales?
Yeah, I mean, there were two surprises that came out of this for me. One was that I had been trained not to sample things with sulfides in them and to avoid them, right? Which is what a lot of people do in drill core, right? Like trying to get a representative geochemical analysis, you shy away from the sulfide. And here we were forced to. because we were limited on the material we had. And so Sally sampled all 3 of these pieces from this depth interval, and then this ended up, that was just a total surprise to us. The second surprise was the thing I showed about heterogeneity of sample powders, and that we weren't actually getting them repeatably measured, because I had also been trained that we should get the same value every time, and we weren't. And so initially we thought that was some sort of issue with the way we were, like there was some analytical issue, but there wasn't an analytical issue. I went through all the data very carefully. So yeah, I do think what this might be suggesting is that we might look at sulfide textures and try to figure out if we can say this is an early sulfide texture. Maybe this is going to hang on to the rhenium in a way that we want it to, right? I don't know about silicate veins. I think if we go back to this figure, just give me a second. By Mond et al., you can see here, there's a silicate vein over here, this kind of like bluish gray. The rhenium, I think, looks like it's enriched at the boundaries of this, which to me is worrying, because it's saying there's fluids flowing through here, and the rhenium is precipitating out or coming out at the contact with the organic matter. And so I think you can remobilize rhenium associated with that, but I don't think I would trust silicate veins. I mean, there's no place in the silicate vein that's actually binding up the rhenium and hanging onto it, right? I briefly explored trying to date black cherts with rhenium-osmium because there is organic matter in them, but the things that we tried didn't have enough rhenium enrichment in them to feasibly date them, unfortunately. So yeah, but it's a great question. I think that is the right way to start thinking about this, is maybe we should be looking at some of these early diagenetic cements.
I mean, like, have people done it in banded iron formation chert lamina, you know, for example? Well,
that was what I was hoping to work up toward, which is why I was interested in the black cherts. But I think in banded iron formations, you might have even less rhenium enrichment, but I think it's going to be really different. It's going to depend on the basin. It's going to depend on the productivity. And so it could be different from one place to another. We tried it in the Gunflint because we already had an age constraint there. And so I thought that was a good test case scenario, and it just didn't pan out. But
Oh, interesting. Okay.
Yeah, well, I was really excited about it and very disappointed, as you might imagine. But
yeah, thanks. All right. If anybody has any other points of discussion, questions, please go ahead. I'll give a few seconds for that.
I know Bob Kreiser and his student tried to do dating on that information, and it wasn't successful. So,
yeah, I emailed Kreiser about this. So for rhenium-osmium, the chemistry is crazy. It's like unlike any other radiogenic isotope chemistry I've ever done, right? You have to seal things in Carius tubes. And so you're limited by the amount of sample powder that you can put into a given Carius tube. And so I thought maybe we could do like 10 Carius tubes and then combine them all in the chemistry later and do the dissolution separately, and then you could get a larger amount of sample. And I was talking with Rob about this, and we ultimately decided it was probably not a viable way to go down this, but it would be a way that you could work with something really low concentration and start analyzing it. But I think the precision that you're going to get out of that is just not going to be very usable either.
But rhenium and osmium are chalcophile elements, so they should concentrate in sulfides. So it might be interesting kind of to try on pyrite nodules, like if you get a sample with multiple pyrite nodules, you can kind of pick up these nodules and see if you get spread on isochron, and you can this way.
Yeah. In the context of a lot of sulfur isotope data and other data, yeah, that could be really interesting.
Okay, well, I really enjoyed this, Annie. Thank you so much. Really good discussion, everybody. Yeah, thanks again, and we'll see you all next week for David Catlin.
All right, thanks for having me. Thank you, everybody.
Thanks. Bye.